Swayam Prabha. Digital India. Educated India.
In the last class, we discussed Cohen-Kuhn technique. We discussed the algorithm on Cohen-Kuhn method. So, today we will solve one problem based on this Cohen-Kuhn technique. I mean, we will determine the tuning parameter values of the controller using this technique. The closed loop block diagram is given with the transfer function of controller as GC equals KC 1 plus 1 divided by tau is plus tau ds. This is the transfer function of PID controller. Then as we discussed, the final control element and controller block are disconnected. So, that is shown here. Then the final control element output goes to the process having the transfer function Gp equals 1 divided by S plus 3 whole square. This is the transfer function of the process. Output of this block is y bar. Then this output is measured the measured signal is then compared with set point value. So, this is basically not the closed loop block diagram, we have disconnected here. Suppose a unit step change is introduced in the controller output signal. Input a unit step change introduced in the input signal to the final control element. So, this is the process. First, we need to form the transfer function of the process reaction curve. So, transfer function process reaction curve PRC is equal to Ym bar divided by C bar, which is equal to Gp Gf Gm. For simplicity, we have considered Gm equals 1. Similarly, we will consider Gf equals 1. Similarly, we will consider Gf equals 1. Fine. Now, if we substitute the individual transfer functions Gp, Gf, Gm, then we get Gprc equals 1 divided by S plus 3 whole square. Fine. So, this is the transfer function of the system, example system. As mentioned that a unit step change is introduced in the input signal to the final control element. So, the process, this transfer function becomes not transfer function, this output becomes 1 divided by S plus 3 whole square, when C bar S equals 1 by S. Fine. We are just substituting this C bar S equals 1 by S in this process reaction curve. Now, we basically need the Ym in time domain. So, for that we need to expand into partial fractions. I mean, we can write this as A1 divided by S plus 3 plus A2 divided by S plus 3 whole square plus B1 divided by S. Fine. In the next, we need to determine the values of these coefficients A1, A2 and B1. So, finally, we will get this form Ym bar S equals minus 1 divided by 9 S plus 3 minus 1 divided by 3 S plus 3 whole square plus 1 divided by 9 S. That means, we got A1 equals minus 1 by 9, similarly A2 equals minus 1/3 and B1 equals 1 by 9. Fine. So, the determination of these coefficients is left for you. So, this is the ultimate form of Ym bar. Next, we need to take the inverse of Laplace transform. Take the inverse of Laplace transform. If we take the inverse of Laplace transform, then we get Ym in time domain as Ymt equals minus 1 by 9 exponential of minus 3t minus 1/3 t e to exponential of minus 3t plus 1 by 9. So, this is the expression of Ym in time domain. In the next step, we need to determine the difference derivative, first derivative and second derivative of ym. Find the first and second derivative of ym. The first derivative of ym represented by ym dot equals t exponential of minus 3t. Check this. First derivative of ym we get as t exponential of minus 3t. This is the first derivative. Now, the second derivative we obtain as ym. Here superscript we have used 2 dot. Exponential of minus 3t 1 minus 3t. This is the second derivative. Fine. The location of the inflection point is obtained by setting the second derivative equals 0. The location of the inflection point is obtained by setting the second derivative equals 0. So, if we do that, then we get t equals 1/3. Fine, this is the root of interest in this problem, t equals 1/3. So, the point of inflection occurs at t equals 1/3. Point of inflection occurs at t equals 1/3. In the next step, we will determine the slope of the tangent line. The slope of the tangent line through this point is S equals first derivative at t equals 1/3. Find the value. The expression is t exponential of minus 3t. If we substitute t equals 1/3, then we obtain 0.123. The slope we obtain 0.123. I think at this stage it is good to draw the response. This is time and this is YMT. So, at this point t equals 1/3. This point corresponds to t equals 1/3, means this is the point of inflection, point of inflection. Now, this point represents the dead time. This point represents the dead time. Fine. Now, the slope we obtain is 0.123. So, this is the process reaction curve. Can you find the corresponding Ym value at t equals 1/3? Find the corresponding Ym value at t equals 1/3. We have the expression for Ym, that is minus 1 by 9 exponential minus 3t minus 1/3 t exponential minus 3t plus 1 by 9. If we substitute t equals 1/3, then we obtain this, which is equal to 0.0294. So, the Ym at t equals 1/3 we obtain 0.0294. So, this is 0.0294. Fine. Now, it is obvious from this plot that 0.0294 minus 0 divided by 1/3 minus Td equals what? Slope. It is obvious from this figure that this equals slope. Now, slope is how much? 0.123. From this correlation we can determine the value of dead time. From this correlation we can determine the value of dead time. How much is that? 0.0943. So, we obtain the dead time 0.0943. Can you determine the ultimate value of Ymt? We represent the ultimate value of Ym by B. So, B equals, how much you calculate? Ultimate value of Ymt, that is limit t tends to infinity Ymt 1 by 9. Now, we can determine the gain k. We can determine the gain k. K is equal to B divided by A. B is the ultimate value of the response and A is the magnitude of the input function. So, B we obtained 1 by 9 and A is 1 because we have introduced a unit step change, that means this K is 1 by 9. Next we need to determine the time constant tau. Next we need to determine the time constant tau, which is represented by B by S. Now, B we obtained 1 by 9 and S is 0.123. So, it gives 0.9033. So, tau is 0.9033. In Cohen-Kuhn method, basically the response of chemical processes subjected to step input can be approximated by the response of first order plus date time system. So, accordingly we have determined the K, tau and Td. Now, what controller we have used? PID controller. They have proposed the expressions for Kc, tau I and tau d as the function of this K, tau and Td. Like for PID controller, the expression for Kc is represented as Kc equals 1 by K, tau by Td multiplied by 4 by 3 plus Td divided by 4 tau. So, we know the values of tau, Td and K. Substituting those values, we obtain Kc equals 117.2. Substituting the values of K, tau and Td, we obtain Kc equals 117.2. Similarly, the expression for tau I has the form tau I equals Td 32 plus 6 Td by tau divided by 13 plus 8 Td by tau, which is equal to 0.222, and the derivative time, which is equal to Td 4 divided by 11 plus 2 Td by tau. And we can calculate this tau d equals 0.0336. Fine. By this way we can tune the controller using the Cohen-Kuhn technique. Next we will discuss the frequency response analysis of linear systems. Our next topic is frequency response analysis of linear processes. So, we need to consider a linear process. when the linear process is subjected to a sinusoidal input. This is a linear process. When this is subjected to a sinusoidal input, its ultimate response after a long time is also a sustained sinusoidal wave. It can be proved that when a linear system is subjected to a sinusoidal input, its ultimate response after a long time is also a sustained sinusoidal wave. A naught are the amplitude, omega is the frequency, and phi is the phase lag. So, this is the input which has the amplitude A. This is the output which has the amplitude A naught, and this output is out of phase by phi degrees or radian. This is representing phi, phase lag. Fine, these are two waves. Now, it is obvious that both the inputs and outputs are sinusoidal, and the output is out of phase by phi degrees. The output is out of phase by phi degrees or radians. The ratio of output and input amplitudes, the ratio of output and input amplitudes is known as amplitude ratio. A naught by A is represented by AR, which is amplitude ratio, and phi is called the phase angle. Phi is called the phase angle. Now, this amplitude ratio and phi both vary with omega. How the amplitude ratio and phi vary with omega is the main concern of frequency response analysis. Amplitude ratio and phi values vary with omega. Now, how the amplitude ratio and phi vary with omega is the main concern of frequency response analysis. Now, we will discuss the fundamental frequency response result. The fundamental frequency response result. A complex number denoted by Z, whose real part is A and imaginary part is B, can be expressed as Z equals A plus JB. Z is the complex number. Now, in the complex plane, we will locate the Z. So, this is the real part A and this is the imaginary part B. Now, the magnitude of Z we can find as magnitude of Z equals root over of A square plus B square. Fine. And argument of Z which we can write by this, and it can be determined using this form. I mean, argument Z equals tan inverse B by A. Fine. This is the argument Z. Fine. Now, for a particular process, we usually have the transfer function. For a particular process, we usually have the transfer function Zs. Now, if we substitute S equals j omega, then we get frequency response transfer function. Replacing S by j omega, we obtain frequency response transfer function. Fine. Now, amplitude ratio we can determine, I mean the amplitude ratio is the magnitude of this Zj omega. Amplitude ratio is the magnitude of the frequency response transfer function. Similarly, the phase angle phi is the argument of this frequency response transfer function. It can be represented by this notation. Fine. So, this is the fundamental of frequency response result. Next, we will discuss the general procedure for frequency response, for finding the frequency response. General procedure for finding the frequency response. First, we will discuss in general way, then we will take few examples to find the frequency response or to analyze the frequency response. Say Gs is the transfer function of a process fine. Now, input to this process we can write as u bar s and output is y bar s. In the first step, we need to replace s by j omega. In the first step, we should replace s by j omega to obtain the frequency response transfer function. This is step 1. Substitute s equals j omega and find the frequency response transfer function. In the next step, represent this frequency response transfer function in Cartesian form. Represent this frequency response transfer function in the Cartesian form. That means j omega equals real part plus imaginary part multiplied by j. Now, by this way we can clearly identify the real part and imaginary part. This is step 2. In step 3, we can determine the amplitude ratio and phase angle. We know amplitude ratio equals root over of square of this real part plus square of this imaginary part. Fine. We can determine amplitude ratio using this. Similarly, the phase angle we can determine from this, where phi equals tan inverse imaginary part divided by real part. Fine. So, you just substitute s equals j omega to get the frequency response transfer function, then represent that frequency response transfer function in this form. I mean, just you try to find out the real and imaginary part. After doing that, use these two expressions to obtain amplitude ratio and phase angle. Now, the alternative technique, in the alternative technique we can represent the frequency response transfer function in polar form. Fine. So, we can represent the frequency response transfer function in polar form, amplitude ratio exponential of j phi. Now, we can write this frequency response transfer function as j omega equals the numerator divided by the denominator part. Now, we will apply the polar form. I mean, we can write the numerator as amplitude and then the exponential term. Similarly, we can write the denominator as first the magnitude of the denominator multiplied by the exponential term. Fine. This is amplitude, this is magnitude of this numerator multiplied by this exponential term. Similarly, for the denominator, this is the magnitude of the denominator d and this is exponential term. Now, this we can write again as numerator magnitude divided by denominator magnitude exponential j n j omega minus j d j omega. Fine. The polar form of the frequency response transfer function we have written here, amplitude ratio exponential of j phi. Now, we will compare these two. Then we obtain the expression for amplitude ratio as amplitude ratio equals this, the magnitude of n numerator divided by the magnitude of denominator, and we obtain the expression for phi also. Fine. So, we can determine the amplitude ratio and phi by this way also. Here the steps are: substitute S equals j omega to obtain the frequency response transfer function. Then you represent the frequency response transfer function by this form, this numerator by denominator. Then use these two expressions to determine the amplitude ratio and phi. So, we will take one example to find the frequency response, I mean to discuss the frequency response analysis. So, we will consider if first order process, first order system. The transfer function of a first order system suppose is given as Gs equals k divided by tau s plus 1. K is the steady state gain of the first order system and tau is the time constant. Now, you proceed step by step. In the first step, we need to replace S by j omega. So, we will substitute S equals j omega. Then we can write z j omega equals k 1 divided by 1 plus j tau omega. Fine. So, we can write this again as k multiplied by 1 divided by 1 plus j tau omega 1 minus j tau omega divided by 1 minus j tau omega. Can we write this? So, this is equal to k 1 minus j tau omega divided by 1 plus tau square omega square. After substituting S equals j omega, we obtain this form. Fine. Now, we need to represent this frequency response transfer function in Cartesian form, that is step 2. In Cartesian form, we can write the frequency response transfer function as g j omega equals k multiplied by 1 plus tau square omega square minus j tau omega divided by 1 plus tau square omega square. We can write this from this expression. Now, we need to find the real part and imaginary part. So, if you compare this with this, we obtain the real part as this. Real part equals k divided by 1 plus tau square omega square. Fine. And comparing these two, again we get the imaginary part also. Imaginary part is equal to minus k tau omega divided by 1 plus tau square omega square. Fine. So, we obtain in step 2 the real part and imaginary part. In step 3, we will determine the amplitude ratio and phi using the expressions. How much is this? Amplitude ratio is equal to k divided by root over of 1 plus tau square omega square. Fine. Similarly, we can determine the phase angle phi. Which is argument and this phi equals tan inverse imaginary part divided by real part. Substituting imaginary and real part, we obtain minus tan inverse tau omega. Fine. So, for a first order system having the transfer function G s equals k divided by tau s plus 1, we obtain the expressions for amplitude ratio and phi representing the frequency response transfer function in Cartesian form. Similarly, we will represent the transfer function frequency response transfer function in polar form for finding the amplitude ratio and phase angle. The frequency response transfer function we obtained as j omega equals k divided by 1 plus j tau omega. Which can be written as n j omega divided by d j omega. Fine. Now, what is n j omega? N j omega is equal to k. So, we can write this k plus j multiplied by 0, and we can write the denominator as 1 plus j tau omega. Fine. Then the magnitude of n j omega is how much? K, and argument is equal to tan inverse 0 by k, which is equal to 0. So, we obtain the magnitude and amplitude for the numerator. Similarly, for the denominator, we obtain the magnitude as 1 divided by tau square omega square. Agree? The real square plus imaginary square whole to the power half, and the argument is equal to tan inverse tau omega. Now, we know the amplitude ratio is the ratio of two magnitudes, magnitude of numerator divided by magnitude of denominator. Then we obtain k divided by root over of 1 plus tau square omega square, and phi is equal to argument of n j omega minus argument of d j omega, which is equal to tan inverse tau omega. Now, these two expressions we obtained also by representing the frequency response transfer function in Cartesian form. Fine. Okay, thank you.